Mr. Isaac, just a quick introduction before we move to your presentation. He began his career as tire engineer and has more than 30 years of experience in product development, OEMs, and manufacturing in India and Europe. He has played a key role in shaping the passenger radial tire development in Apollo Tyres, and he has also an European patent in tire design and has few pending patent applications in India. Mr. Isaac has publications in SAE and other international magazines in his name as well. Mr. Isaac, over to you.
Thank you, Divanshu, for this nice introduction. And it was a very good morning, ladies and gentlemen. It was a very interesting panel discussion. So first of all, I thank SAE and the Mobility Outlook CEAT official for giving us this opportunity to present this technical presentation. And so let's start. Today I will be speaking about the effect of tires on vehicle. So for any vehicle, tire is the only contact with the road. You can have an excellent car, but only these four tires decide, the four contact points, especially if you take a car, these four contact points that decides how the car is going to perform. So the function of tire can be, the tire has multiple roles to play, like carry the load, transfer the braking and acceleration torque, keep the vehicle stable while negotiating by generating all the needed lateral forces. And of course, the tire also needs to perform in an economic way. And the tire will decide how, even if you have an excellent car, the tire decides how the tire will enable the car to extract the full potential of the vehicle. In this, tire is an engineered product, but this is also, but sad to say, this is also a product which is least involved by anyone. So before I start the presentation, I would like to share about a bit about CEAT. 1 minute, let me open the presentation. Hope you are able to see my screen.
Yes, Mr. Isaac, we can see.
Okay. Fine. So CEAT is a part of RPG Group. RPG Group is a more than $3 billion conglomerate. We have a business interest in this one, infrastructure like transmission, power transmission, EPC, etc. That's one of our company KC. CEAT is into tire. Sensor is basically a software company which has presence across the world. RPG Life Sciences is a pharma group with very specific life-saving drugs. RPG Drychem is into engineering products, and then Harrison Malayalam is one of our the agricultural group, which is one of the biggest producers of tea, rubber, cardamom, etc. In addition, there are a lot of other smaller companies which are specifically targeted at something like seniority, which is taking care of the needs of elderly people. So coming to CEAT, CEAT is one of the leading tire companies in India. It's in India for more than 50 years. It's quite strong distribution network, 4,500 dealers, 500 exclusive dealers across India. We have 7 manufacturing facilities. Chennai being the last one we have added in 2020, which is one of the, it's growing pretty fast. And we are also exporting to more than 100 countries, including Europe. Currently, the revenue is over $1 billion US, and this is expected to grow much faster. We are also ranked among the top 25 companies for Great Place to Work. So this breakup of the product, we are present in all the product category, and 61% is our replacement share. Export accounts for 13%, OEMs account for 26%. If you look at the product category, we are present in almost all the products that are in the automobile part. And so now we have our R&D center. Since it's a technical programs, I will talk about R&D. So we have our corporate R&D center in Halol near Baroda in Gujarat. and our European Technical Center is in Frankfurt. We have two test centers, one in Natrax in India, a dedicated area, and also in Europe near to automotive testing test track, ATP test track in near to Germany. So when we talk about test, let's come to the subject now. So since the time Sumerians invented the wheels 5,000 years ago, while the shape remains the same, the applications have changed significantly. First pneumatic tire was in 1888, and radial tires were commercialized by Michelin in around 1950. In fact, pneumatic tires have revolutionized the transportation. And today, if you are looking, we are passing through an area where the concept of mobility itself is changing, and also the tire is also changing. Tire is moving from pneumatic tires to non-pneumatic tires, tires with the sensors that can communicate, that can control, and the list goes on. But the good thing, as I told in the inaugural day, at the moment, every vehicle will have tires. Vehicle may change, but tire also will change, but there will be a tire. Now, if you look at the evolution of automobiles, I classified them into three. Then it's the source of energy, involvement of human, speed, power, and application. Because all the three will have impact on the tires. So the evolution of IC engine to fully electric or the hydrogen fuel cell. This is one of the major reasons is the environmental issues that we are facing. Automotive industry contributes 13% of the total carbon emission. So the vehicles are changing. So also the tires that are needed for electrical vehicles. The involvement of people in driving when it moved from level 0 to level 5. The involvement of people are also at level 4 and 5. The driver is not required actually. So in that time, the role of tire is getting changed from what it was to today, and also the power and application. All these things have significant impact on the performance requirement on the tire. For example, battery electric vehicles are inherently heavy. They do not have any engine noise, and they have high torque. So the tire needs to withstand, tire should have a capability to carry the higher load, which should be able to withstand the high torque, and also needs to be silent so that the ride will be comfortable. So when it comes to the autonomous driving, when it comes to level 4 and 5, so where the human intervention is not there or the driver himself is not there, then the reliability of tire is important. The tire cannot have any failure, tire cannot have any puncture, and it also needs to monitor its own health, so that the proactively some corrective actions can be taken. And also the speed, power, and application, when it's changed, the handling characteristics or the ride characteristics, everything changes. And also a car like Bugatti, which can go 400 kilometers plus speed, kilometers per hour plus speed. So the tire that is needed for that is completely different from a normal tire, which all of us know. So this means, so the tires of the future, if we have seen some of the drivers that are bringing in the changes. So the future mobility is, at least in the urban side, is going to be multimodal, connected and shared mobility. This means the tire also needs to have its own capabilities. Like tire also must be able to talk to the vehicle, talk to the cloud, talk to the owner, and it's become an active part of the control. So tire is a connected tire. We have seen the environmental part. The tire needs to be sustainable. Sustainable means European Union has already brought in regulations. So by 2030, 55% of the tire needs to be made from sustainable material, and sustainable material also is having certain specific definitions. So it needs to be lightweight, it needs to have long life, it needs to be retreadable, recyclable, and low rolling resistance, airless, the list goes on. And when it comes to this autonomous driving, the tire needs to be puncture resistant, puncture proof or self-repair, airless, and durability. All these are the other requirements that are coming. The tire industry is also evolving along with the auto industry. So all this means there is a change over a period of time. The performance requirement of the tire is changing. In the past, when the handling was not very important, then it was comfort and noise first initially, and recently comfort, noise, handling become important. And in future, since autonomous driving is coming in the picture, so it's going to be the comfort of the people. People are not more involved in driving, so they are doing other activities. So the comfort inside the cabin is going to be more important. So you have seen the fuel efficiency, because fuel efficiency have moved to the most one of the most important characteristics in any vehicle, in a tire. So if every vehicle is having a set of active and passive safety technology built in, and this also has evolved over a period of time. This is a long list of items like brake system, seat belt, airbag, ABS, ESP. So the list is quite long. However, if you look into any of the active safety features, tire is a part. So that means for the active safety to work in a given vehicle, the tire performance critical. So the tire needs to be tuned for that particular vehicle. So this also means the tire that is tuned for a given vehicle may not be the right one for another vehicle. Depends on the characteristics of the vehicle. So we have seen how tires and tire characteristics have an integral part in the active safety system. Tire also plays a critical role in the ride and comfort of the vehicle as well. Tires having significant contribution to the mechanical and acoustical comfort of the vehicle. For example, and also these some of these requirements are conflicting in nature. For example, a tire which is very good in comfort may not be the best in handling. A tire which is very good in noise may not be the good in aquaplaning. Hence, tire development is an act of balancing conflicting requirements, yet provide an exciting experience to the customer. Now, I would like to talk about something what we are doing in CEAT when we do this development, and how we tune the tire characteristics to meet the vehicle performance. Let's talk about ESP. The driver gives a steering input, which we can expect multiple inputs. The tire can have a rollover tendency, or tire can slide in the vehicle. However, since the vehicles are equipped with the ESP kicks in and bring the vehicle back to the normal, for the vehicle to continue continue normally which is under control. In which some various systems comes into play. Tire characteristics plays a key role here. We achieve this in CEAT through the tire engineering part, wherein we decide on the shape of the it's basically the basic engineering of the product, basically the shape of the tire, the footprint, the tread pattern, the selection of material, so all those things. It's quite a long engineering activity, and that is followed by evaluating the product in laboratory and also in vehicle for the objective measurements. And then finally it is verified verified on this by the subjective evaluation. So this is quite a long process, and today we are trying to create a relationship between objective measurements and subjective measurements. So far we have been successful in many of the area. There are still some gaps, but wherever we have established this objective to subjective correlation, it is easy for us to take the decision at the objective level itself. This also saves a lot of time and money. So now we'll talk about vehicle dynamics envelope. So this is not only the tire, wheel, or suspension, it's the vehicle in totality: the body, the steering, suspension, wheels, and the rims. So now if you look at the different vehicle parameters, it can be the handling stability, the braking effectiveness, the ride comfort, noise characteristics, aquaplaning. These things are part of the the vehicle dynamics and performance. So now we look at the handling performance. So this has two parts: the driving pleasure, which is basically the feedback to the steering, feedback to the driver, or the how fast the vehicle responds, and vehicle responds to the steering input. A good a good handling car is a fun to drive. The right feedback from the steering gives the driver the confidence how fast you will be able to that gives him the confidence how he can enjoy confidently, he can drive the vehicle. The second part is on the grip and the response. This is basically the acceleration and braking, whether he is able to stop the car at the desired distance, or in case of an emergency, whether he will be able to manage that. So as I told in the previous slide, when we develop a product for a given vehicle, we evaluate different tire constructions, materials, compound, etc. And prototypes are prepared, and then they are tested in the laboratory for parameters like cornering stiffness, alignment stiffness, footprint pressure distribution, static stiffness. There's a host of parameters, and then if there is a reference tire, especially when we work with an OEM, OEMs normally give us a reference tire. So we compare it with the reference tire. If it is meeting or close to that point, then we take the vehicle for the vehicle with tire to tire for the evaluation on vehicle for objective and subjective measurements. And these parameters, for example, cornering stiffness is an indication of steering response. Alignment stiffness is responsible for how fast it is, the vehicle will be able to come back to the straight line. So some of these relationships are these are direct, some of these relationships are derived. So and when you talk about the cornering stiffness, a normal car, a family car, need not have a very fast response to like a racing car. For example, we don't want a lady who is driving the car with children in the backside, and if she looks back, the smaller steering input should not create a major deviation in the vehicle path, whereas that is needed in a smaller steering input. Sorry, a smaller steering inputs need the very precise movement in case of a race car or a handling oriented car. And then so we as I told in the previous slide, we were also evaluating we are also doing a study how we are able to connect the subjective versus subjective objective measurements to the subjective measurement. Some of this success that we have achieved is shown here. There is more or less some major things only we have shown here. Your response to steering response, steering torque, steering feedback, lateral due to tire grip. And there are in some cases, there is no relationship also. The last one, understeer gradient, understeer feed. So we could not establish the relationship. And this the objective measurements can be either on the vehicle or on in our lab on flat rack machine or other stiffness measurements, etc. And when it comes to braking, braking, the graph here shows, the graph here shows the slip ratio versus mu for three different tire, the same tire with three different compound. Basically, this is an actual study. This is three different compounds with three different peak mu values. So the mu, the friction ratio, the friction coefficient is a function of compound and assisted by the tread pattern, footprint shape, footprint pressure distribution, etc. So the basic thing is coming from compound, so we can measure the compound in our lab. So we have a machine called the lat 100. From the lat 100, we can establish what is going to be the grip potential of the compound. We can rank them, and then then when the tire is made, we can do the same mu slip measurement on our flat rack machine. And then the same thing again, either in the flat rack machine on the actual application condition, we can measure it on a traction trailer. And then finally on the vehicle on finally the testing on the vehicle. So here the relationships we could establish very clearly. So a higher grip compound tend to give a better braking distance. So it's an empirical relation, thumb rule, but we could establish is 20% improvement in mu slip value. The peak mu value is giving us around 2-meter improvement in braking distance. So these are all part of our part of our development. But okay, it's while it is improving the braking potential, but we also need to ensure this is not leading to a higher wear or higher wear or higher any other issue. So now when it comes to ride, as we know, there's a constant push for reducing the weight of the vehicle, primarily to improve the power to weight ratio, fuel efficiency, cost optimization, etc. We also know that reducing the weight of the vehicle, weight of the vehicle increases the undamped natural frequency, which means more road shocks are transferred to the vehicle body, which makes the ride unpleasant. The stiffness of the tire plays a key role, and also the damping characteristics of the tire. So both we can measure. We have we have a high-speed uniformity machine which with the cleats in it. So in which we can actually measure the damping coefficient, and also on the stiffness measurement, the static stiffnesses can be measured, and also from the flat track, the dynamic stiffness, with which we will be able to predict how it is going to perform in the vehicle. Now, the ride is normally having two parts: the mechanical comfort and the noise comfort. The tire road interaction creates two sorts of noise, which is basically the structure-borne noise and airborne noise. Structure-borne noise transmits to the inside the cabin through the structure, and airborne is through the outside through the air. Normally, structure-borne noises are classified up to 500 Hz, and anything above 500 is considered as airborne noise. There are multiple mechanisms for the noise generation. The air in the cavity, the air inside the tire cavity creates cavity noise with very specific values, which we can actually theoretically calculate, and it's very easy to identify but difficult to correct. Then the sidewall flexing is sidewall related the sidewall induced vibrations and noise. The tread patterns inside at the tire and at the contact area acts like a pipe, and it creates a pipe resonance. And the tread pattern, when it hits the road, it creates a tread impact. That also is specific to the tread pattern, and which can be calculated and can be corrected. And the leading edge of the footprint and the trailing edge of the footprint, this will have two different noise. And also, since this is a horn, the noise that is generated at the footprint is amplified due to this horn effect. So it's basically a very complex system. Complex. It's very complex, and it's you need a lot of knowledge to correct it. And then also the airborne part. In addition, this noise that is generated at the footprint, that noise generated by the tire at the tire because of the tire road interaction, also creates environmental noise. Especially this is critical when we pass when it is impact the health of the people, like people who are staying closer to highways, or when we pass through the forest, when it affects the animals. So the government puts very strict control regulations on this pass-by noise, as we all know, whereas in-cabin noise is specific to a given vehicle. So this is and how do we correct this? This is one case study, the real case study. So we had an issue. So we didn't find a correlation between the test tracks in India and the test tracks of the OEM, which was abroad. So then we actually measured the tire contact patch noise close proximity measurements in the leading edge and trailing edge, and then we could establish the relationship. So this in-cabin study, tire contact patch noise study, and then based on this we did the modification. We repeated the study, and then finally when we had gone back to the track, we were able to achieve the required target. So initially the difference was something around 2.5 dBA in the high frequency noise, and which we could bring down to 0.4 dBA. But okay, further we worked on it. We could correct the problem, and then we came out of we could get the approval. This is a real case study. Aquaplaning, as all of us know, this is basically depends on the compound characteristics, the wet grip of the compound, and also the major contribution is coming from the tread pattern, how fast the tire is able to remove water from the contact patch. So normally we measure two types: longitudinal, wherein the car goes straight, and lateral, when the car negotiates a curve. So you require two different test tracks to do this. These are the these are the actual tests. I will show you a video also how we are doing this. In case of longitudinal aquaplaning, it is easy that we can look at the speed at which the aquaplaning kicks in. And in case of lateral aquaplaning, we look at the maximum lateral G that is achieved. So when we look at that was on the measurement, how we have the capabilities within CEAT. So we are equipped for all these measurements, objective way, whether it is steering characteristics using steering robo, dry handling, wet handling, and the instrumented vehicle for ride part, and the noise measurements or the fuel efficiency. Some of these you have already seen during the track day on 17th. So and that was on the objective measurement part. And then when it comes to the laboratory side in the indoor testing, so we are equipped with the MDS flat track, wherein we can characterize the tire for handling, braking, and we can also do the tire modeling, because we have a fairly good CAE team, a finite element simulation team, and we are already working with some of you as partners in your development. We are ready to work with you for ready to work as a partner with you for more of your work. And we have a high-speed uniformity machine. This is a special machine which is equipped with the cleats for ride simulation, anechoic chamber for indoor noise measurement. So this is a very complex, compact system, and we are able to use it very well for our development. Rolling resistance measurement, durability, tire wear analysis. Tire wear analysis, we are also able to even predict the heel and toe, and throughout the 360 degree, how the footprint is changing with respect to or with wear. So we are able to simulate. This is a fairly good indoor facility that we have, and we are still planning to invest more for some more equipments. So we are open to work with the OEM customers as well. So where are we testing these tires in India? We are working. We are doing all our testing in Natrax. And past we used to use VRDE. VRDE has come down recently, of late. And then with the international circuit, when we actually need for extremely high speed evaluation, but now with Natrax coming in, this also will come down. And Madras Motor Sports Club in Chennai. In Europe, most of our activities are happening in ATP in Germany. This is a test track near Bremen. And in winter, we go to Idiada because of the weather. Germany will not be able to use. we have a product range for as I said, we are having we have a winter and all season product range specifically for Europe. These tires are tested in Arctic folds in Sweden, and specific durability testing we do in Germany. The team in CEAT consists of people with experience and correlation with most of the OEMs in India and Europe. I have a small video on how the actual testing is done. This is a video we recorded recently in our European test center. So you will see here mostly our Europe colleagues. So, but it covers all the almost all the it covers all the test all the track level testing that we do. So I will play here.
All our tires are tested exclusively in the lab, and thousands of test miles are driven to ensure our tires meet our customers' high expectations. For testing lunar conditions, of course, we are using. Of course, we are following all by law by our customer. Tires have changed significantly in the last 5 years. Sustainability, the rolling noise, driving comfort, driving aspects, the safety aspects, the fuel consumption, and also these requirements will become stronger. We, as a tire company, CEAT, we are following safety requirements globally. We have committed ourselves to create and to produce tires from highest performance, quality, and safety standards. CEAT supplies all types of tires for all types of vehicles, thanks to our expert teams. With the CEAT Tyres Unit.
That's all from my side. Thank you for this opportunity. Hope this conveys what is expected.
Thank you, Mr. Issac. We do have a couple of questions. We have about 5 minutes to go for the next presentation. So let's take a couple of questions. One is from Ajay Sankaran. Ajay wants to know, how can we change tire stiffness in airless tires?
Okay, so there are multiple approaches to the development of airless tire. So one is what we see normally in terms of what we can see, like the Michelin Optis or Michelin Optis or the Peel. So basically, we can change the stiffness of the springs inside, that's plastic springs inside. That is how it is achieved, and also the changing the material.
Okay. S. Mohan has a question. He wants to know, is there any relation between the slip ratio and tire torsional stiffness?
Slip ratio is basically on the straight line. Torsional stiffness comes into picture with the stiffness of the sidewall, etc. So may not be a direct relation, but okay, the higher the tire which has a higher torsional stiffness will definitely improve the mu value.
Okay. All right. So I have another question from the same gentleman. How can we improve braking feel by tire characteristics? Which parameter of tires do we need to measure for the subjective brake feel?
Okay, so there are two. We need to look at two situations. One is the ABS or the non-ABS. In case of ABS, what we need to improve is the ABS setting and the tire peak mu values. They are in sync. They should match. If they are matched, so then you will get the best braking performance and the feel. In case of block braking, which practically no vehicles are there, then we'll have to look at the stiffness of the tread and also the characteristics of the compound.
Right. Thank you. I'll take one final question for you, Mr. Issac. This is from Anbarasan Mani. Mani wants to know how much percentage is the impact. So what is the percentage of impact of tread pattern on tire friction coefficient? Is there any difference between an IC engine and electric vehicle tread patterns?
Okay, yeah. So it's two questions. One is on the this impact of tread pattern on the friction coefficient. Friction coefficient primarily depends on the tread compound. Okay, so then the thing is, definitely there is an impact on especially on dry braking. The tread pattern is having the tread pattern, especially the grooves. The grooves is having an impact on the grip potential or the braking performance, which that depends on the tread pattern. So you cannot increase especially in a summer country like India, we cannot increase too much of lateral grooves because it increases the wear of the tire. So it's basically a balance. So I will not be able to say what percentage, but basically there is a balance that we need to hit. And on the second question, on the difference between tire for electrical vehicle and IC engine tire, yes, there is a difference because as I told in the presentation, there are three things that we need to see. One is the rolling resistance of the tire, because a lower rolling resistance tire will increase the driving range of the vehicle. So it has to be a lower rolling resistance tire. Second thing is the electrical vehicles are inherently heavier compared to comparable IC engine. So that means the tire must be able to withstand that higher load. So it's normally going for a higher load rated tire. So we are, in fact, in Europe, people are talking about XXL tire. So the same tire size remains the same, but will be able to carry a higher load. European Union has already brought this standard XXL load standards in Europe last year. Third thing is on the resistance, and okay, and also on the torque of the initial acceleration, the torque of the vehicle is very high. So you can achieve 0 to 100 in less than 4 seconds, 5 seconds. That's the kind of, even on a I personally drove some of this vehicle. It's very fast, and that means the tire must be able to withstand that initial torque without any slippage. So the stiffness, normally when we develop a tire for IC engine, there's a balance that we need to achieve between the longitudinal stiffness and the lateral stiffness of the tread pattern. So that we need to alter here. So here it should be able to withstand a higher longitudinal force that is coming. So the stiffness parameters that needs to be adjusted for this one. There are a few differences between like this between IC engine tire and electrical vehicle tire. IC engine tire you may not be able to use because of it will wear out. It will not be an economic. You will not be able to enjoy. But the other way it is possible.
All right. Thank you, Mr. Issac, for that very detailed and very insightful presentation. I'm sure our participants today are going back richer with knowledge, and thank you also for answering some of the questions that our attendees had. Truly appreciate your time.
Thank you.
Before we move on to our next presentation, may I request Vivek, my colleague, to play a video from the track days. Thank you. Thank you. We now move on to the final presentation of today's conference, as well as this conference called Motion and Control. We have with us Professor Pim van der Jagt. We're truly honored to have you. He's a technical director at AB Dynamics Europe, GmbH. Pim has over 30 years of experience within the automotive industry, including 22 years at the Ford Research and Innovation Center in Germany, where he has held various senior management positions in vehicle dynamics, chassis engineering, and driver assist active safety systems. Before this, he worked for the Goodyear Tire and Rubber Company, where he studied tire vehicle interaction using computer simulation and instrumented vehicle testing. Pim, welcome to Motion and Control. Over to you.
Thank you. Thank you for the introduction. Welcome. Yeah, you will receive the handout material. I took a lecture that was part of Ford's Vehicle Dynamics 2 course, and there's also a lecture at Cologne University and Loughborough University. It's in total 89 slides, which is way too much to fit into 1 hour, so I reduced it significantly. But in the handout you will receive all 89 slides. So this can already skip. I already gave a pretty good introduction of my previous career. Before Ford, I was at Goodyear, and I studied in Delft. I studied with Professor Pacheca, the famous professor for tire modeling. So I was one of the last students of him before he retired. But I say the total lecture contains all these parts of the tire: steering, handling, uniformity, comfort and ride, a lot about tire wear and rolling resistance. I had cut off the presentation for today. I will only talk about steering and handling and the uniformity part. But as I mentioned, in your handout material, all the slides are available. And if you ever want the long version of the presentation, I'm also available to do that. But then, as I said, normally it takes at least 3 to 4 hours. Yeah, the previous presentation was also about tires, so I don't know exactly how my presentation compares to the other one, and if there's not a lot of overlap. That's unfortunate. So I will talk mainly about the tire from an OEM manufacturer side, what we do, especially at Ford, to optimize tires for a new vehicle. You know, normally during the development of a new vehicle, shortly before the vehicle goes into production, an OEM goes to several tire submissions to optimize the tire for a new vehicle. Normally in Europe, each vehicle will have at least 3 to 4 different suppliers for the tires. In the US, it's more normal to have only 2 suppliers, even for very high volume vehicles. But in Europe, there's a lot more suppliers used. In the old days, it was quite normal to go to even sometimes up to 10 different submissions of the tire before it was fully optimized. Nowadays, because also the reduced number of prototypes and reduced development times, they go to a lot less development cycles and also try to do a lot more, not only by actually physically building the tires and testing them, but also do more and more CAE. So you have several tuning options of the tire, and the first and probably the most important one is the mold shape, and basically determines how the roundness of the tire. And you can change a lot of the characteristics of the tire by changing the mold shape. Unfortunately, the mold shape normally tends to be fixed very early in the development program, because building a mold is quite expensive and takes also quite some time. Now with 3D printing, some of the prototype tires are built in 3D printed segmented molds, so that is the turnaround of getting a new mold is a bit quicker than in the old days. So once the mold shape is fixed, you can play a lot with kind of the thread material, the layup of the belts, and then the distance between the belts, and also the reinforcements in the sidewall. And basically that you can try to get an optimized tire for handling, steering, ride, and also rolling resistance. I know it was already mentioned in the previous presentation. At the moment, especially in Europe, rolling resistance is the most important criteria. And the rolling resistance target gets fixed very early in the program because it has an influence on the fuel economy of a vehicle. So it is important for electric vehicle to extend the range, but it's at the moment, because of you need to reach your average fleet CO2 target, and there to have minimal rolling resistance tire is a very important factor there. So now they fix normally the rolling resistance at very low levels, and that limits the kind of the freedom you have to optimize the tire for other characteristics, especially for steering and handling. Yeah, I will talk about, when I talk about steering and handling, I will talk quite a bit about lateral force, longitudinal force. I didn't see the whole previous presentation, and I imagine that if I talk about aligning torque, braking force, that most people are aware what they are and what direction is involved. So in the steering and handling, I will now mainly talk about lateral force, longitudinal force of the tire, and also the aligning torque. We'll talk about quite a bit, because that's an important factor also for the steering feel of an OE tire. Yeah, in that talking about steering and handling, we also talk quite a bit about the slip characteristics of a tire. So in the lateral way, there's a top view of the tire, and the velocity vector of the wheel center will not always be in line with the plane of the tire. So if there is a lateral slip, you have a slip angle, which is determined of the angle of the vector of the forward direction of the tire and the speed velocity of the wheel center. On top of that, you have wheel slip in longitudinal direction to generate traction or braking forces. And that is a kind of slip in the contact patch that is defined as the forward velocity of the wheel center minus the rotational velocity and the rolling radius. The radius used here, the geometric rolling radius, is not always the same as the loaded radius, so the actual distance of the tire to the ground. The rolling radius is normally a bit more than the loaded radius, and will lie below the actual rolling geometric radius, will lie below the road surface. To measure the steering and handling characteristics of the tire, and a standard machine in the industry that is used and is available at practically all tire manufacturers and several automotive OEMs have this machine, and some universities. It's built by MTS, and it's the MTS flat track. The flat track is a steel belt that normally gets coated by a type of abrasive surface, normally GM safety wall. And there you can measure all the tire characteristics. You can imagine that the friction properties of that surface are different from the actual road. But testing tires on the road is very difficult. If you test a tire on the road, you'll get quite a bit of variations depending on weather conditions, temperature, and all kind of other external factors. So the repeatable testing of tires on the road is very difficult, and that's why most people, if they compare tires, test them on these MTS flat track machine. During the testing, if you prepare the tire well, you do certain preconditioning test and then kind of keep control of the temperature during the test, you can get very repeatable testing. And if you retest the tire several weeks later or you only get a few % different in the measured characteristics. If you test on the road, you will get quite high differences between from test to test if you test a few weeks later. Still, sometimes for modeling, some road testing is done, and several tire manufacturers, universities, and institutes also have road test devices, normally built in a truck before it's the heavy weight, and with a test wheel in the middle, and then they are able to go out and go on every surface. At Ford, we sometimes have even taken those trucks to let's say, north of Sweden to test under ice and snow conditions. And also most of these trucks have a water spraying installation, so you can test on the controlled water conditions. So you have a kind of controlled layer of water before the tire if you start testing. So to really get an understanding what tires do, and under other conditions than dry, so in the wet and ice and snow conditions, you really need to go out with a test tray. So a lot of these of outdoor road testing is done to build proper or better simulation models for the vehicles. But to compare tires and tire characteristics, most of the testing is done in the laboratory on those MTS flat track machines. So what characteristics are then normally measured, and then are the most important ones for steering and handling? Is of course the lateral force characteristic, and what I said, unfortunately, I don't know what was discussed in the previous presentation. Lateral force is normally the tire for small slip angles is very linear. So we call that the cornering stiffness of the tire. So these are all the test conditions here are under one constant load. So the tire is then very linear and then flattens out, and almost that very large slip angle stays flat and doesn't dramatically drop off. So even up to very high slip angles of 30-40 degrees, the level of lateral force will almost stay constant. The difference is now longitudinal force, and that at first is also linear, much stiffer normally in longitudinal direction than in lateral direction. So normally the longitudinal stiffness of the tire is about 1.5 to 2 times higher than the lateral stiffness. It will reach a peak and then drop off. And that is also what ABS control does. You try to stay, to generate maximum braking force, stay around this peak level point. The region after the peak is really an unstable region. If you stay there, the tire will go instantly to full lock. So full lock is minus 100% braking, and this is 100% traction. Then I said the self-aligning torque is a very important characteristic. Again, that reaches a maximum and then drops off significantly, and then even changes direction. I will later show a deformation distribution of the tire, or the slip distribution in the contact area, to understand why it has this type of characteristic. This characteristic you can feel very well if a vehicle is very much understeering. You know with steering you can reach so much side slip on the front wheels that the aligning torque changes direction, and you lose all feedback torque in the steering. And sometimes you cannot even release the steering, and the steering will stay in the steered position, or even steer itself to a larger angle. On the set, aligning torque is difficult to tune, but has a very large influence on the initial steering feel of a vehicle. Now with EPAS steering system, in the old days, the aligning torque was very important, and you could only do a little bit with correcting with the assist torque. But now with EPAS steering, you can artificially do a lot. If you don't really like the torque feedback, you have much more freedom to optimize it in the steering than only optimizing it in the tire. And then a very important characteristic is if you have both a slip angle and longitudinal force. So this is a condition where you put the tire, that's also possible on the flat track. You put the tire on the 4-degree steered angle and then start braking or start driving the tire. And then you get this characteristic. So at first stays almost constant, but then at high braking or traction levels, the tire will drop and even go to 0. That's also one of the reasons to have ABS. If you go into full lock, not only you lose braking performance because you had a lower longitudinal force point than before, but you also then lose all directional stability. So basically you cannot steer and control the vehicle anymore. That's why an ABS is normally working to keep the tire in this region, so you have full kind of lateral force capability of the tire during braking and traction. It is exaggerated a bit here. Normally this is seen as a circle, but normally a tire tends with very low braking, the lateral force normally goes up, so you get a bit higher lateral force, and then only at high braking levels it will drop off significantly. It's a bit exaggerated in this plot, but that is a normal trend for tires, that slight braking forces increase the lateral force. Because I mentioned before, you will have quite significant different friction properties depending on what the type of road surface is. And here you see a braking characteristic of a tire. So the normal one, as I showed before, the red line, in the normal dry conditions, a well-defined peak and then dropping off. And here you see also an ellipse that defines if you have ABS control and what region you try to keep the tire. So this is under wet conditions, and wet asphalt, if the water layer is not too thick, you almost have very good still friction capabilities even under wet conditions. Of course, if you start aquaplaning and the water layer gets too thick, it will drop off significantly and can even get very low or almost 0 if you really start aquaplaning. So you don't have the same contact pressure of the tire with the road surface anymore. Then you will have this type of situation. But this is under only marginal wet conditions where you still have full road contact. You can still reach quite high friction levels of the tire. Then ice, I will first talk about ice before I go to snow. So ice has very low friction levels, and also for ABS, you need to have a very fast control on the polished ice to keep the to keep the brake from locking. So we need a very fast ABS control, and with old systems that was sometimes very difficult, and they tend to wander out to very high slip ratios and then had to come back completely. So you lost a lot of brake performance. But now the systems are much faster and much better controlling. You try to also keep really the maximum, also even when it is not very much under icy, polished ice condition. So snow is something special and has a very particular characteristic there. If you go to full lock, you tend to go up significantly in friction on snow, but then again, you can't really steer the tire anymore, so it's not desirable. For short brake distance, it would be desirable to fully lock the tire, but that is not good for directional stability. So On snow, the ABS control goes to much higher slip ratios, but never goes to full lock, even when it's possible to achieve more friction. This characteristic is if you lock the tire on the snow, you start plowing the snow in front of you. That basically generates more longitudinal force than if the tire keeps rolling. But what I said, it's undesirable to go into full lock under packed snow conditions. I mentioned it before that I want to briefly explain with some physics how aligning torque is generated. So at low slip angles, if you have the contact patch area, this is the lateral slip distribution over the contact patch. So this for low slip angles. If you go to higher, you see it gets more even. There's maximum friction here, and then more and more of the total contact region goes into its maximum generated slip force. And then if you kind of at even higher slip conditions, you start what we saw before, but with the longitudinal force, you start dropping off in force at the area that has the highest slip velocity, and then you start kind of getting to this distribution. So you see this, the center, the arrow points the kind of center of the force distribution. So first is in front, and then kind of you want to turn back the tire to a straight ahead position. Then it wanders almost to the center of the contact patch. So then you will reach zero aligning torque. And at very high levels, it will even change direction. And then you get this aligning torque characteristics that I showed before. So this is the start with small slip angles, higher slip angles, and then a change of direction if you go to very high slip. So I mentioned before that original equipment manufacturers go to a lot of submissions to come with all approved tires. So there's a real example of the old, it's already quite an old plot, but to show these were for original equipment Mondeo tires, 2 different sizes, 2 different manufacturers. So in this case, it was Goodyear and Michelin, I think, yeah. So you see there's quite a bit of difference in the tire characteristics of these tires. But subjectively, by the OE test drivers, these tires are all lying in a subjective rating range on a scale to 1 to 10, in around between a 7 and an 8. So they're all approved tires, and the average customer will not even notice the difference between those tires. They all perform well for steering, handling, ride, and will all have similar rolling resistance levels. As you can see, the characteristics of the tire vary quite a bit. Also, the subjective measurements, this is, for instance, a steady state cornering, so like steering wheel angle gradients and understeer gradients. There's quite a bit of variation. So this is test results and simulation results. So you see with simulation of the tires, but it's all tire characteristic measured on a flat pack. And then measurements carried out on normal proving ground, so Ford's proving ground in Belgium. And you will see that you have quite different understeer gradients on the different OE tires, but they all perform well. So to mention, the overall level is not what determines the performance of a tire is the overall balance, so the front rear balance and a kind of the control feedback to the driver. So you can have still quite well performing tires that have significantly different characteristics, and most of the performance is determined between the balance front and rear of the tires. This is a plot where I show, before I mentioned what friction level difference or what characteristic differences you have between a real proving ground and the MTS flat track. So these are characteristics of a tire measured at the what I said, Ford's normal proving ground and on the MTS flat track. And the normal trend is we always use the test on 3M safety walk, is that the friction levels at a proper asphalt road surface tend to be higher than what you measured on the flat track. So there is methods, you can find it in the literature, to scale tires to get more accurate grip levels on the proving ground. So you can always take laboratory measured tests of tire models and scale them, scale the stiffness and scale the overall friction. That's very easy with Pacheco's magic formula to get the same levels as on the test track. So that enables you to get more accurate and more better absolute numbers in your simulation. Like this was simulated with not correcting the tire friction levels, so it was pure flat track data measured for these simulations. You see like understeer gradients, because kind of both front and rear are changed in the same way. You see simulation and measurement read the same absolute number for this characteristics. But if you, for instance, go to the slip levels of the tire, then you see there is quite some difference between simulation and the measurements. But you see the trends that you see in simulation are still there in the road measurements, only the absolute levels are quite different if you don't use the correct scale data. So use the scaling for the road surface you're testing on. Again, here, this is not the full letter of force characteristic. This is the characteristics of cornering stiffness. So the linear part of the tire in newtons per degree slip against vertical load. And again, you see it's 4 approved tire constructions from a Ford product, and you see there's quite some difference in the cornering characteristics. Here, see the same characteristic that I showed before for 3 different inflation pressure levels. And there you can see that basically inflation pressure is a very big factor. And then test drivers or expert drivers, especially tire testers, can normally change the inflation pressure from the rear and get a tire that doesn't perform well by changing the pressures from the rear in a certain direction, can get a tire to work well on a vehicle. So if you start tuning with inflation pressure, you can almost get any tire to perform well on a vehicle. Unfortunately, normally on vehicles, the inflation pressures for certain vehicles are fixed, and there's not much you can change there. And some OEMs or some manufacturers even prefer and mandate that the inflation pressures from the rear are the same. They make that easier for customers to keep the correct inflation pressure. But most of the time, it's better to have different from the rear inflation pressures to get a better balance in the vehicle. So again, inflation pressure is a big tuning factor, but normally it's fixed by the OEM manufacturer. But by playing or lowering a bit from the rear, you can get a different balance in the vehicle, and sometimes do some more further improving of the vehicle's performance. Here I'm going to show now what effects certain tuning parameters of the tire have on the performance. So we always start off with an approved tire that is set for all these different important characteristics. So you see all different requirements there are for it. So there's ride performance, steering, handling, stability, dry braking distance, grip level, wet performance is a requirement, rolling resistance is normally fixed. Then there's a wear requirement. Noise is very important. You need to have a resistance against potholes, so that not if you hit a severe impact, the tire gets damaged or the rim gets damaged. And now also more and more, because it has an effect also on fuel economy, is the weight of the tire. And then truck rut sensitivity is if you have a road where the track where the truck drives, you normally get a bit a non-flat road surface, and in some countries it gets pretty bad. And then you have some tires that start wandering between. You have difficulties driving straight because they keep wandering in those truck ruts. So in this, we did at Ford we did an investigation if you only changed a tire manufacturer normally does that, but we only change one characteristics of the tire. So in this case, we only change the construction stiffness. And the target was to improve ride. So you kind of improve the ride performance by about 3%, but you see that you have very significant degradations. If you start optimizing the construction stiffness for ride, they'll probably reduce the construction stiffness to improve the ride. And you lost quite a bit, especially steering performance of the vehicle. So there's still in tires, there's always these trade-offs. If you start optimizing in one direction, that you lose performance in the other one. So this is the tread pattern changes. Again, make it more a softer tread pattern. And again, you reach a small improvement in ride of 2%, but with very significant penalties in steering and handling performance. In this case, you see also with a softer and less stiff tread that the truck rod sensitivity is improved. So outer is always better, that the truck rod sensitivity is very significantly improved. And here the tire contour, again, I mentioned a rounder contour of the tire, so more round tires, better for ride. And then again, the stiffer, so with straight up sidewalls is better for steering and handling. And again, here you improve the ride, and then you see how much trade-off there is with steering and handling and the other characteristics. And also here, in this case, with rolling resistance. And then the same for tread compound. So that gives you an idea what the trade-offs with the different tuning components you have in a tire. If you only change one of them, what normally the impact is on the performance, on other performance elements like steering, handling, ride, what the different trade-offs if you start optimizing one or the other. So this is an example of it's a bit an older picture already, but it still gives you the kind of different characteristics of the tire. So a European summer tire is normally constructed this way. It has normally a solid or quite stiff center rib, also for steering. Then for handling performance, this is the outside shoulder. Normally get very high, wide, stiff outside shoulder blocks. Sometimes even without any openings in them. But that, of course, the openings are there to get some wet performance. But with real high performance tires, sometimes don't even have a very solid outside shoulder, even get a better limit handling performance. I want to set very wide, big blocks and very stiff. Then winter tires really have the very thin sipes, and I show you later how they are constructed. So they're very flexible tread blocks. There's also, if you drive in snow, a lot of the snow gets stuck in the tire. Like in this tire, if the tread is clean, you still have some performance in snow, but very quickly all these wide openings get stuck with snow, and then the snow stays in there, and then there is no friction anymore. So here you make the tread block so flexible that they keep moving and lose the snow if they deform. So very weak tread blocks. If you drive those tires in dry, warm conditions, you very quickly start wearing out those sipes, and they kind of start deforming. You get a very strange shapes if you drive these tires in the dry conditions. And then an all-season tire is a mixture of that. It doesn't have these very thin sipes that you see here, but has some more flexibility. And then the outside shoulder blocks are a bit stiffer, so you have a reasonable performance on the dry conditions. So in Europe now, for all-season tires get more and more popular because sometimes mandated in certain countries to have winter type tires or all season tires, and people don't like changing the tires or forget to change, and some people even drive their winter tires in summer while they don't have time or don't want to change, and then you have kind of very bad summer performance and also a lot of tread wear. So the all season tires get more and more popular. So in the US, always most tires and about almost, I think, 85% of all OE tires are all-season tires. But now in Europe, all-season tires are also getting more and more popular for original equipment. Now, I mentioned these sipes in the winter tires, and they are very complex constructed forms. So if you look into them in two directions, they have a very shape. So they keep moving, and they make sure that no snow can get stuck, or if snow gets in there, that it is released. So a North American all-season tire has not the 3-day shapes that is the real winter tires have. That they have the linear sipes, and then they don't go to the full depth of the tire. So if this tire wears, you lose the sipes completely, and also you have then very poor snow and ice performance left. Again, I mentioned it already in speaking, but here you see it in a matrix, how normally they are constructed. So summer tire, very stiff shoulder block, stiff center, and no traction edges. And then here you get softer. And you see what the trade-offs are in performance. So dry performance, summer tire is perfect. And then you lose performance if you go to all season, or even winter tires on the dry handling are normally is very poor. So I come to the last part now of the steering and handling, and that's an important fact. It's not a tuning parameter, but it's very important if you simulate a tire. So the characteristics of the tire I showed before, so the lateral force, longitudinal force, aligning torque, is what we call steady state characteristics. So they are measured under a very slowly changing slip angles or longitudinal slip. If you change very fast, the tire has a delay. So there is a relaxation length, as we call the tire. So kind of the force lags. So this is a slip angle. The steady state characteristic would generate this force. But if you change it fast, the tire force is lacking the input. So there's about a first order delay in the tire. So this is the characteristic of a step response. So you instantly put the tire on the step and then start rolling it forward. And then the tire takes time to reach a steady state level. So we call that relaxation length, and that is very often measured. And also it's really needed to have accurate dynamic simulations like frequency response testing or a lane change. It's important for your simulations to include the lacking effect. So the relaxation length of a tire is important to include that. There is a way, if you can't measure it, there's a way to have a reasonable estimation of the relaxation length. And you can, so there's this first order delay in the formula shown there. So you can estimate the relaxation length if you know the cornering stiffness from your flat track test, and you measure the real lateral stiffness of the tire. So putting the tire flat on the road and then pulling it sideways, and then you have a real lateral stiffness of the tire. So if you divide the cornering stiffness by the lateral stiffness and then extract half the contact length, you have a reasonable estimate of the relaxation length. So if you don't have any possibilities to measure relaxation length, there's still ways to estimate this relaxation. Relaxation length is important. Will have quite a bit of effect on the handling performance, but it's difficult to use it as a tuning parameter for a tire. And here you see some radically different tire, quite some different tires, but different cornering stiffness levels. You see the relaxation length in meter doesn't vary that much. So with a reasonable estimate of the relaxation length in your simulation models, you can have a reasonable simulations and simulation result. So that brings me to the end of the part on steering and handling. As I said, there's a lot more examples in the handout and a lot more slides in the handout package than what I use today. So now I get to a part of the tire that creates most problems for OEMs and sometimes creates a lot of customer complaints or sometimes even recalls or changes in in the vehicle to get some effects under control, and that's uniformity of the tire. So what I want to talk about is about conicity and ply steer of a tire, residual self-aligning torque, run out of the tire, the force variation, and all rolling circumference variations. I will talk about how you need to control them and also why you need to pay attention to with tires. So the first effect is conicity and ply steer, and it's basically if a tire runs perfectly straight ahead, like you would run it on a flat track or a drum, you have an offset force in the tire, and this offset force in the tire is built out of two effects. One is ply steer, and that's caused by the belts have a certain angle relative to the tire, so the steel belts, depending on how they are laid up and what the angle is, you generate ply steer. Ply steer has the effect if you run it in one direction, the ply steer will be, for example, to the right. If you then run it backwards, it's to the left. It's quite a high force, but it generates, it changes direction if you change the direction of travel. And then the other effect is really conicity, and it's a bit exaggerated here. It's really the tire is not a perfect cylinder, it's a bit of cone, and that will generate a force. And this force, really, if you change the running direction, it will always stay in the same direction. And that's really how you can measure it. You first roll the tire in one direction, measure the offset force, and then run it in the other direction, and then you can calculate the conicity and the ply steer with these. So this is really done for every tire that is produced, OE tire. After the production line, it's put on a rim, or it's two half rims, it's inflated, put on a roll, rolled in two directions, and then these values are measured. I mentioned ply steer is a very high force and conicity a much lower force, but ply steer, because the belt angles are very accurately positioned and they're all the same, it's a high force with a very small force distribution. So it's always the same force, and it really doesn't cause a problem. Because ply steer is the same on all four tires, and what a vehicle does, it will actually have a little angle relative to the driving direction. So normally I draw this on the board to explain it, but it's so online it's a bit more difficult to explain. So if you only have ply steer in the tire, you have quite a high force that is the same direction on all tires. Because if you put one tire on the other side, the rolling direction changes, and then the ply steer is again the same. So a vehicle puts itself on a small angle relative to the driving direction. It's only an angle probably of 10 or 2/10 of a degree, and then the forces are equaled out. So then there is no residual force anymore, and the tire and the vehicle drives straight ahead. It's not perfectly straight because we'll have a little angle of 2/10 of a degree, but nobody will notice. So ply steer takes itself out by putting the vehicle under a little angle while driving. A lower force, but a much bigger problem is conicity. And here you see the distribution. Because the distribution, you can have quite high conicity on one side, and you can't really it's not really so conicity is much more important to control, and you need to put very low levels. If you have tires out here with a high conicity, you can have that on one tire. That tire can cause the vehicle to not drive straight. Or if you drive straight, that you have a residual aligning torque in the steering. So you constantly need to steer to go in a straight line. But that's why the OEMs put a limit on the conicity of the tire, and every original equipment tire is measured if the conicity is below the required level. So here again, you see what I'm talking about. That this again the full characteristics of a tire, and you see at 0 slip angle you will have an offset force. So I will zoom into it, and the same is true for the aligning torque. So now I zoom into only that center of the tire. So here you see the lateral force, and here's the aligning torque. So it is important what is said. So you have this offset force that is corrected by putting the vehicle under an angle. So you go to this angle, and then the force is 0. So if you control that on all tires, the vehicle put itself under an angle, and the forces are equaled out, and the vehicle goes straight. But then on the tire, if the force goes to 0 and the aligning torque is still too high, the vehicle goes straight, but you still feel a moment in the steering. And then it's very, in the old days, it was very nerving that you then constantly had to steer to go on a straight line. So there was also, in OE tires, there were requirements for the residual self-aligning torque in a tire, and it had to stay below a certain level. So the target at Ford was between 0 and -3 Newton meter. So we only work in the minus direction, because if you drive on the right side of the road tends to have a slope to the right to get water off the road. It's a very small slope, but a negative self-aligning torque kind of makes the vehicle drive straight. So if you control that at these low levels between -3 and 0 residual self-aligning torque, you will not have any residual torque in the steering. So in the old days, as I mentioned, with hydraulic power assist, it was very important to have control over this residual self-aligning torque levels and make sure that the tires were in this range from 0 to -3 Newton meters. Nowadays, EPAS steering systems have algorithms to automatically detect that if you're driving on a straight line, that there is a residual torque left in the steering. And it can automatically correct for that. So now you have an option to avoid this complaint or customer issue by having an automatic correction in the steering system if this occurs. So now I get to the non-uniformity. So every tire that is mounted, and there is a mass concentration, for instance, somewhere in the tire, you spin it on a balancing machine, and you put a balance weight in, and then on the balancing machine there is no force variations anymore. So it's a perfect balanced tire. But does that solve all the problems you have with tires? No, it doesn't, because if it's really a mass concentration in the belt and you start putting that tire on the road, so on a load, then if the tire has a distributed stiffness around the tire that's the same, and you have this mass concentration here, if you start running it, you still get force variation. So balancing alone is not enough, and that's again the reason that the OE tires are after production are mounted on a rim and run on a drum to really check out the force variations you have on this tire. And again, they will have requirements. Original equipment manufacturer will have requirements for the tire that the force variations need to stay below a certain level. So the mass concentration in the belt is not the only problem you can have. You can also have get imbalances because the tire is not perfectly round. So then you have a once per revolution force variation in the tire again. Or again, you have the belt, for instance, don't exactly match, but they overlay, and then you get another effect that creates that you have locally a bit higher stiffness than the rest of the circumference. And then you get a force variation, that you get a pulse in the force if you if the stiffer point of the tire runs to the contact patch. So I mentioned this is how it's done in the tire production. The tire is mounted, 2 half rims, grab the tire, it's inflated. Under a certain controlled load, it's put on a drum, and a load cell measures the force variations both in radial, so the load, and lateral and longitudinal. So then you get a characteristics like you get a force variation like see here on the plot, and then normally in the production machine already there's fitting done of the first harmonic, the second harmonic, and third harmonic. So most of the time all OEMs will have limits on the first harmonic of the force variation that needs to stay below a certain level. So normally those levels are fixed, and if all tires are measured and are below that level and released for production, you will not have any issues. But sometimes already when the vehicle is in production was found out that even when tires were delivered, they were below the limit that was given, that there were still vibration issues, just because the vehicle was too sensitive for tire force variation. So that's why normally, if a tire goes into production, or if a vehicle is fully in production, you do these tests. So you create an imbalance in each individual tire, and then start kind of increasing the imbalance in a tire, and then you start running at what level you get vibration issues. So normally this is a real case, so it was done perfectly, no force variation, and an imbalance of certain gram. These are grams imbalance, so that's 40 gram imbalance and 80 gram imbalance. So you started off, and then you were seeing when the tire, when the vibration or when it got unacceptable, and you had to check in this case if it was about 40 degrees imbalance, caused vibration issues in the vehicle, that is acceptable. But if you notice that already at, let's say, 10 or 20 grams imbalance, the vehicle was getting vibration issues, then you know your vehicle was too sensitive. And very likely in production, you would run into significant customer complaints about vibration of your vehicle. So then it was necessary to go back, retune some of the suspension bushings to make the vehicle less sensitive for tire imbalance. And I said, if you know your vehicle is not too sensitive, and then in the production tire is measured, you control most effects and you will not run into any vibration issues. That's true except for one, and that's the tangential force variation. So the measurement in production, this test that I showed you before, is only done at very low speed. So a slow rolling speed to measure the force variation, tangential, radial, and lateral. So that is normally at this low speed level, and a limit is set, and the tires are delivered that are below this limit. So for the radial and lateral force variation, if you go up in speed, they will not go up very much. So by controlling the limit at this low speed and using only tires that are below a certain level at low speed, you have these effects under control. But the tangential force variation, which is basically a non-uniform rotational speed of the tire, if you start driving faster, you need to accelerate and decelerate the tire faster and faster, generating very high longitudinal tangential forces. And that can also create, if you have tires with issues in that area, you will also create high-speed vibration problems. So this is not something you can fix in the vehicle. That needs to be fixed by the tire supplier. But again, then normally these effects only show up if the tire is already in production and you start running into customer complaints for vibration. You need to start looking at the tires, and then sometimes the tire needs to be, the design of the tire and then the construction needs to be fixed to stop these tangential force variation vibration. So normally if you have these issues, it's with only one of the release constructions. So then you can just for a short period stop delivering tires with that construction, and then still keep using the other tire suppliers that don't have those issues. So this was basically all I preferred for today. Still saw a lot of questions, so there will still be a lot of questions. So we have plenty of time now for Q&A. And as I mentioned, in the handout is another part on right rolling resistance and tire wear. Thank you.
Thank you. Thank you, Professor Jagt. Truly appreciate your presentation. We indeed have a lot of questions coming in. Let me take a couple of them one by one.
Yep.
Deva Ranjit, he wants to know how tire pneumatic trail affects the low-speed steering returnability.
Low speed steering is the characteristics I showed are all for high speed. At low speed, you have different effects. There is what they call turn slip effect. So that's another characteristic that normally you need to separately measure and also model. So modeling tires at low speed is completely different from modeling tires at high speed. So what I said, you need to then include turn slip effects, and then you can only really ask to look at the returnability of the steering. Again, the industry has, I need to drink something, my throat is getting a bit blocked. The industry has changed a bit. In the old days, the tire had a big effect on the returnability of the steering and was very important. And sometimes some tuning of the hydraulic boost characteristics, steering geometry, and tires had to be done to get proper steering return under low speed conditions. But nowadays with EPA steering systems, all of them have active return. So suddenly the tuning the tire and also tuning your steering geometry is not that important anymore, because actively control of the EPA steering can now make sure that you have a proper and tuned return of the steering to a straight line.
All right. We have a question on how to define the static and dynamic imbalance for a motorcycle tire.
I'm not the big expert on motorcycle tires, but I also don't know if these tires are also measured. I can imagine that also there the OE tires are measured if they leave production to make sure that also there the force variations stay below a certain level.
All right. So the other question is, what is the contribution of tire stiffness resonance for response in ABS control?
Yeah, that is quite a bit effect. But yeah, the softer the tire is, the easier the control gets. And what I said, in the old days, with the non-analog valves, it was not so easy to do a good slip control. But the modern ABS system with analog valves, normally they can do a much better control. So they can react much faster and have a much better pressure buildup. So it's easier than also very stiff tires with a very defined peak to control them around that peak area. So in the old days, with all the systems, it was much more difficult with tires that had a very sharp drop-off to keep a reasonable control. And very often you have very wide slip variations where you lost quite a bit of braking distance by the ABS control. But again, big improvements have been made and the systems are now able to react much faster than in the past.
Okay, Professor, we have one final question. This is about what causes the tire wiggle when F1 corners at high speeds. Mm-hmm. So it's okay. Is it the cause of Scalamek waves?
Again,
what causes the tire wiggle when F1 corners? So it's probably asking about in Formula One, what causes tire wiggle at high speed? High speed cornering.
And F1 tire is a very unique tire and has some particular characteristics. Because tires are not the best for handling. So artificially, an F1 tire is only 13-inch tire with a very wide diameter. So these sidewalls are relatively soft. So with the high forces and high loads that are on this tire, you get very high deformation of those sidewalls, and also at really high forces, sometimes you get vibration in those sidewalls. So it's really next year they will go to a much more different tire dimension, different tire. They go to bigger rims with lower sidewalls. So very likely next year the performance of the tires will significantly improve because they have a better kind of shape for high performance and for higher lateral forces. So the high sidewall is really very disadvantaged. You only have one tires to get the proper performance out.
All right, thank you, Dr. Pim van der Jagt. Truly appreciate you answering the questions from our attendees today.